Hello again. Welcome back. Today we are talking about, and I know you can't hardly see it over here, but the atom guys. These lovely fellas that we talked about on the last set of notes in the brief history of the atom. So yesterday, last day's lesson, all you had to do was write this down. Today, we're going to actually take notes on the atom guys. And I figured you would rather fill in the blanks than to write down all of that stuff. So the first thing that you should do is the quick review that covers the last set of notes. So in notes 1B, we talked about matter, we talked about compounds, we talked about elements. So you've got this word bank down here at the bottom, and you were supposed to use the word bank to help you to answer and fill in the blanks of the quick review at the top. We are going to have quick reviews on every single set of notes from here on out, so get used to it. All right, so you needed to use the word bank to fill it in. So an atom is uncuttable, the smallest part of matter. An element is on the periodic table, and some combination of them makes up all matter. An element has only one capital letter in its chemical formula. A compound has two or more. A mixture can be easily separated. A compound can't be easily separated. All right, so now we're going to talk about all of our different atom guys. So who was our first one? I say Democritus. You say Tomos. That's right. So Democritus is our first one. Democritus was a Greek philosopher. He believed that if you cut matter small enough, eventually you would reach an uncuttable particle, and that particle was called atomos, and in Greek, atomos means uncuttable, which cannot be divided, and that is where we get our word atom from. Our next guy was John Dalton, and he was a British chemist, and he believed some things that aren't true. He believed that atoms could not be divided or destroyed, that there was no way to get any smaller than an atom. And then we found out that there are particles smaller than an atom. He also didn't think that atoms could be broken apart, but we learned with the atomic bomb that you can indeed break atoms apart. You're going to get a big boom, and it takes a lot of energy to do it, but it can be done. He said that atoms of the same element have the same mass, and he was correct about that. He said atoms of different elements have different masses. Now, what's interesting here is that he was only partially right. Because of isotopes, you can have atoms of the same element that have different masses. So, for example, I could have 5 atoms of carbon here. And this atom of carbon has 5 protons, but only 1 neutron. And this one has 5 protons and 2. And this one has 5 protons and 3. Well, it doesn't really work like that. It would be more like 5 and 5. We're talking about carbon here, so that's 6. 6 carbon would be 6 protons and then 6 neutrons for the stable balanced atom. But you can have isotopes that have 6 protons and 5 neutrons, or 6 protons and 7 neutrons. It's different mass, but it's the same element. So he was a little off on that one. He said that when atoms combine, they do so in predictable amounts or ratios. You know, from math class, a ratio is where you, how many of this thing to how many of that thing. So if it's a 1-to-1 ratio, then that means that 2 things happen together. He is the marble man. We call him the marble man because our word for when I say Dalton, you say marbles. That's right, because he thought that atoms were like small, solid spheres, like a marble. Next up, I say Thomson. You say, right, muffins. So next up is J.J. Thomson. Now, this is not Thompson. Some people get it wrong and put Thompson, but it's Thomson. He did believe that there were smaller things inside the atom. He was right. He believed, though he was wrong, he said the atom was a positively charged ball, like a round muffin. So as if I was to take my muffin batter and pour it into a snowball mold instead of in my cupcake tin, and I would get a round muffin. And he said that the blueberries were like the negatively charged electrons inside the atom. And then he said the whole atom is neutral because the charges balance out. So, and he was right about that. If I've got 8 neutrons, I've got 8 electrons to balance neutrons. If I've got 8 protons, I've got 8 electrons to balance it out. Whew, I need an editor. Somebody edit my videos for me so I don't have to correct myself like that. I can just say the right thing and cut out the bad thing. Yeah? Yeah? Anyway. And this stuff, all this stuff needs to be deleted. Me erasing and scrolling and all that. All right, so we did Democritus. We talked about Dalton. We talked about Tom. Our next one, when I say Rutherford, you say empty space. That's right. So his name was Ernst Rutherford. The Americanized version is Ernest. So you might see Ernest Rutherford here and there, but his real given name was Ernst Rutherford. And he believed that atoms were mostly empty space. And he was right about that. So that's why we still remember him, because he gave us that idea. And way back before we could even remotely see inside of an atom, he knew that it was mostly empty space. He also said that atoms have a small, positively charged nucleus and negatively charged electrons that fly around it. And he was also right about that. So good job, Ernst. Next one, I say Bohr, you say ring, boring, right? Boring. What's our key word for Bohr? Rings. So Niels Bohr was his name. And his model had rings. So he believed that atoms have energy levels and that they were represented by those flat rings, and those electrons that are outside of the nucleus move in those energy levels. He believed the more energy they have, the farther they travel from the nucleus, and he was right about that. He said the energy levels farther from the nucleus can hold more electrons. He was right about that. His is often called the solar system model because when you draw it out, it looks like a model of the solar system. You have your nucleus in the center, which is like the sun. And then you do your first energy level with the electrons like planets orbiting. And then your next energy level with the electrons like planets orbiting. And it starts to look an awful lot like that model of the solar system that you drew back in the 3rd grade. So that's why it's called the solar system model. He also pointed out that if you change the energy of an electron, its energy level changes. All right, next up is one we don't have a model for, but he's very important. When I say James Chadwick, you say Jimmy Neutron. Right, so James Chadwick is our next important atom guy. And we call him Jimmy Neutron because he's the one that said, you know what? The nucleus of an atom is way too heavy to just have the number of protons that we know are in there. There's got to be another particle that's equal weight, but that has no charge. Even though he couldn't see it, he could tell from the studies that he was doing that something was going on. So did he invent the neutron? No, he discovered the neutron. So he discovered the neutron, and he discovered that it has the same mass as the proton, but no charge. So it is neutral. All right, so now we're here at our modern time. When I say Schrodinger, you say modern, right? Schrodinger. Remember that one, Schrodinger. So just like the other day, caveat that this is just what we currently believe, and that if studies are being done right now that is changing the mind of science about the nature of atoms, then let me know and I will correct myself. But right now we believe you can never know exactly where the electrons are in the cloud at any given time. As soon as you identify, oh, there it is, it's gone. Like before you can say the word, there it is, it's gone. So you can't know where they are. There are indeed energy levels within the cloud. So Bohr was right about that. He said that when electrons change levels, they either give off or absorb energy. And that can be observed as light, can be observed as heat, or other forms of energy, motion, combustion, light, heat, and motion. A glow stick, like I said the other day, is a perfect example of this. The whole reason why the glow stick glows is because there are chemical reactions happening and the electrons are jumping energy levels and it's creating light. Most of the mass of the atom is in the nucleus. So the heavy part, remember how dense in the video, 6.2 billion cars worth of nuclei, right, into a 1 foot box. That's how dense it is. So the heaviness is in the nucleus. And then the size, though, comes from that empty cloud. So the volume comes from the electron cloud. So it's odd to think about, but it's kind of like I took a lead, something really a sprinkle, a lead sprinkle. I took a piece of lead that was the size of a candy sprinkle and then put it inside a balloon and filled it up with air, right? So that's our atom. We've got this very dense center, this very dense nucleus, and then all this electron flying around in empty space and magnetic fields and all of that jazz. Oh, I got this. Yeah, lovely. Okay. The best, most compelling modern model of the atom was proposed by Edwin Schrödinger. So that's why we associate Schrödinger with the modern model. Now, why was his model better? It improved upon Bohr's model because it changed it from a flat model, right? Like if you took Bohr's model, that, thing in the center and then the rings on the outside, if you turn that flat like this, what would it look like? Yeah, it would look kind of like a fried egg, right? It would have like a bulge in the center, or a ravioli or something. Do we look like raviolis? Does the matter around us look like raviolis? Our matter can't be shaped like that as a whole, or it wouldn't work. We know that the whole atom is three-dimensional the whole way around, that it is a perfect sphere and that it's not flat. So while we like Bohr's model because it's much easier to see where the electrons are, here's the nucleus, here's electron 1 and 2, here's electrons, 8 more of them can fit on that ring. And it's so easy, right? But how in the world do you teach that using this model? I don't know where they are, right? So we prefer Schrödinger's model because it is more accurate and three-dimensional like we are, but we like using that flat Bohr model because it's easier to learn from. We use Bohr to learn from. We use Bohr to model. We use Bohr to show where the electrons are staying. But if we want to get an accurate representation of what it really looks like, we're going to use Schrödinger's model. All right, last thing you're going to do for this set of notes is we're going to remember what our keywords are for the 5 atom guys that we have models for. So we don't have a model for Democritus because he didn't really come up with a model, and we don't have a model for Chadwick because he didn't really come up with a model. All he did, he named the atom. All he did. What he did was name the atom, and what he did was discover the neutron. So there really isn't a model to go with them. So these 5 are going to be the 5 that we have models for. So the first one is Dalton. I say Dalton, you say right, marble. And then you're going to draw. If you can, put some shading in there to try to make it look three-dimensional, do. But if not, just give me a perfect circle, okay? I say Thompson, you say, that's right, muffin. And so his model is a positively charged cake with negatively charged blueberries. I say Rutherford, you say empty space. So Rutherford goes next. Empty space is our key words. And for his model, we're going to draw like the more Simpsons model with the nucleus in the center and the rings going around. I say Bohr, you say, right, boring. So ring is our keyword there, and then that means our model is going to be the one that has the rings. I say Schrodinger, you say modern. So our last one is Schrodinger. He gave us our modern model. And this is the one that has the nucleus in the center and then dots. And then those dots are the electrons. And then we realize that those electrons are flying all around and really can't be pinpointed in any one place. All right, that's it for the Atom Guys notes. See you next time.